Okay, so let's continue our discussion related to digital circuit design. And in the last couple of lectures, we were looking at circuits which are called combinational circuits. And in the next 2-3 lectures, we'll spend some time on looking at circuits which are called sequential circuit design. So we had said that a broad classification of digital circuits could be done in terms of combinational circuits, whose characteristics is that the output depends only on the present values of inputs, and sequential circuits which have feedback in them. The output depends not only on the present value of the input but on the past values of input also. All right, so let's look at some of the basic building blocks of sequential circuits. And so let's look at something called a SR latch. And the SR latch that we will see can be implemented using NOR gates or NAND gates. So first, let's look at a SR latch built using NOR gates here. And so the first thing that we note here is this feedback here, that these are the outputs here. These are the output of a gate here, and this is the output of a gate here. And the outputs are fed back to the input side here. All right, so there's a feedback in these circuits. And we'll see that this is a basic memory circuit here. And so how does this particular circuit operate? Okay, so there are two states of this particular circuit. One is what we call as the set state. So set state is where Q equal to 1 and complement of Q bar, is equal to 0. So that's called the set state of the latch. And the other one is the reset state of the latch, where Q equal to 0 and Q bar equal to 1. Okay, so how do we program this particular latch into the set state here? So let's say we put 0 here and 1 here. So this is what we call as the S, or the set input, and the reset input here. So we put S equal to 1 and we put 0 here. So the moment we put 1 here in a NOR gate, immediately the output here becomes 0, and 0 and 0 here. So it puts it 0 and 0 here, puts it 1 here. So the moment we put S equal to 1 and R equal to 0, we are setting this particular latch into the set state here, which is Q equal to 1 and Q bar equal to 0. Okay, so let's write down the description of this NOR latch here. So when S is 1, R is 0, Q equal to 1 and Q bar equal to 0. And the state is what we call as the set state here. Let's do the complementary part here. Let's put this as 0 and R equal to 1 here. So the moment we put R equal to 1, irrespective of whatever is the state here, the moment you put R equal to 1, it goes to 0 here. And 0 and 0 here, then it puts it to 1 here, right? So when we have reset input is 1, then the latch goes into a reset state, and reset state means the output is equal to 0, Q equal to 0, and then the complement part is 1 here. All right, so that's why we call it the set pin here, or the set input here, and we call it the reset input here. The moment you make set active, S is active or high, the output goes equal to 1 here. And the moment you make R equal to 1 here, the output goes to 0 here. Then there is called the hold state here. So once you program this particular latch into a set state or a reset state, well, you can remove the input, and then it's in a hold state, which we call as 0, 0 here. So when it is 0, 0, note that it is in the hold state. Whatever is when you apply 0, 0, whatever is the state of the latch, that state continues to stay in that particular mode there. So for example, if Q equal to 1, then you can see here, this is 1 here, 1 and 0. So that makes it 0 here. And therefore it stays in that particular state here. Similarly, if Q were 0 and Q bar were equal to 1, you would have seen that the latch would continue to stay in that particular state here. So that's why when we applied 0, 0, the output is nothing but whatever it was before, and so it is equal to Q and Q bar here. So that's why we call it the hold state here of the latch. And then there is, when we have two inputs, there is also a possibility of 1, 1 here. And 1, 1, the moment we put a 1 here and we put a 1 here, so note that the moment you put a 1 into a NOR gate, you'll immediately make the output of that particular NOR gate 0 here. And so if you put 1, 1, both Q and Q bar are 0, 0. But that's a state, that's a input, and that's a state that we don't use in a SR latch. And let's go into it, why we don't use that particular one. It's called an invalid set of inputs, invalid state here. All right, so when we put 1 1, so we get 0 0. So both the outputs are well defined, fine, but they're 0. And the problem is that we want one of the outputs of the latch to be Q and the other one to be Q bar. So that rule is violated here. So both are equal to 0 0. But there's another reason why we don't use these two inputs here, R equal to 1 and S equal to 1 here. And that is is that when you remove 1 1 and you go to some other input there, for example, if you take 1 1 and then you go to 0 0, so 0 0 we saw is the hold state here. Well, the output is unpredictable. For example, let's say when you go from 1 1 to 0 0, and note that this R and S can come from some preceding gates here, and they may not change simultaneously. So let's say, you go from 1 1 to 0 0, but what happens is the first bit that you see here, it immediately changes to 0 0, but the other bit, this one here, takes a little bit of time, so it stays at 1, and then because there's a little bit of delay there, so it is in this particular part, there's a little bit of delay here, so it stays at 1, and then after that delay, it goes to 0 here, right? So let's say from 1 1, it's going to 0 0, but it goes through an intermediate state here. Why? Because of, let's say, the different times at which the input arrives at R and S here. And so what happens then? So when you apply 1 1, so this is 0 0, and then what is happening is R is becoming 0 and S is becoming 1. So R is becoming 0, S is becoming 1. So this is like the set input is activated, and so this will go into 1 0 here. And then you go into 0 0 state here, and when you go into 0 0 state here, finally when this S also becomes 0 here, well then 0 0 is like hold state, so my NOR latch has gone into a state of 1 and 0 here, or in the set state here. Okay, fine. So when we go from 1 1 to 0 0, it goes into a set state here. But so Q equal to 1. But it may happen that it's not the S input which is slightly delayed, but suppose it's the R input which is slightly delayed here. Okay, so this is one particular case here. So suppose the inputs change as 1 1 to 1 0, so the R input is a little bit delayed here. And in that case, we can easily see 1 1 0 0 here, and then the S comes earlier, changes earlier, R remains 1. And so therefore it goes to 0 and 1 here, and then eventually R also goes to 0, and it goes to 0 1 here. So the latch then goes into a reset state here, Q equal to 0 here. So that is the problem with applying an input 1 1 here. When you apply an input 1 1 and then you go to, let's say, 0 0, then the output is unpredictable, because we don't know which input is coming slightly earlier, or which input is coming slightly later here. And because that depends on all the previous circuitry which is there here. And depending on what is happening in the previous circuitry here, which input comes earlier or later, the output will then be accordingly. It may go into a set state here, or it may go into a reset state here. So it's unpredictable. And this is not just because of the delays in signal coming to the R and S input. It can also happen, if for example, due to we have two NOR gates here, but the two gates may not have equal delay. Even when you make the gates, we realize are made using transistors, and transistors characteristics depends on doping and the thickness of the dielectric and many other properties that are there here. And these properties vary from one place in silicon to the other place in silicon, and as a result of which no two gates are identical in terms of, for example, the delay that occurs when you go from input to output. So note that when you take a NOR gate here and you change the input here, it takes a certain amount of time for the output to change here, and that's called the delay of the gate here. So let's say the two gates that we have here, they are they have unequal, they will always have some unequal delays here. The delay will not be identical. And so let's see, the same thing, the same kind of an error or same kind of a behavior occurs because of unequal gate delays here. So when you have 1 1 and then we go to 0 0, right? So we are talking about why 1 1 input is not the right input or is an invalid input, because the output is unpredictable. So when you go from 1 1 to 0 0, and suppose gate 1 is faster. So gate 1 is faster here. So we've gone to 0 0. So both the inputs have changed simultaneously to 0 0, unlike the previous case where one was changing earlier than the other. So in this case, let's say both have changed simultaneously, but gate 1 is faster here. So this 0 here goes here, this 0 here goes here, and this gate is faster, so it reacts and immediately it goes to 1. 0 0 will make it 1, and this 1 then is over here, and this one will then keep the this particular output as 0 here. So the output then, because gate 1 is faster, the output, the latch goes into a set state here, Q equal to 1. On the other hand, suppose gate 2 is faster. So if gate 2 is faster here, so what will happen is then this 0, this gate 2 will react first. So 0 and 0 will transform it into a 1 here. And this 1 will go here and keep it in the 0 state here. So in this case, it goes to Q equal to 0 here. So now, depending on which gate is faster, we may get an output which is 1 or output which is 0 here. So again, it's unpredictable. We don't know which gate will be faster or which gate would be slower. And therefore, we do not know what is the state of the latch and what is the state of our this particular memory element that is there here. Okay. And so the output is unpredictable in general. And it's for that reason that we don't use 1 1 state here in an RS. So we use 0 0, which is the whole state here. We can use S equal to 1, R equal to 0, or we can use R equal to 1, S equal to 0. So those three inputs are allowed, but R equal to 1 and S equal to 1, they are not used. They're not used because the output is unpredictable or can be unpredictable. The same thing we can implement using a NAND here. So in a NAND, we take two NAND gates and we cross couple them. We take the output of one NAND gate, put it into the input of the other one, and we take the output of this one and put it into the input of the other one. So this is called cross-coupled, two cross-coupled NAND gates here. And we can see here, so in this case, it's sort of an active low. So when S is equal to 0, because it's a NAND gate, so it reacts to S equal to 0 immediately. So when S equal to 0, then 0 here immediately makes Q equal to 1 and Q bar equal to 0. So my latch goes into a set state here. On the other hand, when R equal to 0 here, when R is 0 here and S is equal to 1 here, so that immediately resets the latch here. And S and R equal to 1 1, one can verify when S equal to 1 and R equal to 1. So when S is equal to 1, this particular gate is enabled, and basically it depends on the value of Q bar here. So whatever is Q bar here, then it turns out to be Q here. So with S equal to 1, one input equal to one input of the NAND gate equal to 1, the NAND gate basically acts like an inverter. And so Q bar goes here, Q bar then becomes equal to Q. So the latch stays in the same state here, and Q goes here and it becomes Q bar here. So it acts like an inverter with R equal to 1. And for the same reason that we discussed earlier, that we don't use 0 0 here. If you use 0, if you put 0 here and you put 0 here, it does go into Q equal to 1 and Q bar equal to 1. So that's something undesirable. But more than that, when we go from 0 0 to, let's say, 1 1 state here, the output is unpredictable. And so the latch has to be used in such a way that when we go from one set of input to the other set of input, the outputs are predictable. For example, if we go from 1 1, if we go from 1 1 to 0 1, well, we know what will happen. Q will be equal to 1. Or from 1 1 to 1 0, we know what will happen. Q will be equal to 0. On the other hand, we know that what will happen is if from 0 1, we go to 1 1. So from 0 1 to 1 1, what will happen? Well, the output will stay equal to Q, which is equal to 1 here. So all that is fine, except when we use an input SR, S equal to 0 and R equal to 0. When we start with S equal to 0 and R equal to 0, and then we go to S equal to 0 and R equal to 1, then it's predictable. From S equal to 0, R equal to 0, if we go to 1, 0, then also it's predictable. But when we go from S equal to 0 and R equal to 0 to 1, 1, then it's unpredictable. We don't know what will happen. And it's for that reason we call these inputs as invalid inputs here, or we don't know, or an invalid state here. So we don't use them. And so note that this is a memory element. We are calling it a memory element because we can store, we can program this particular memory element using this S and R here. So if we want to program this memory element Q equal to 1, we apply S equal to 0 and R equal to 1. And then we remove this input here. So when S equal to 0, and when you remove it, when you make S equal to 1, well, it stays equal to Q, right? It retains its state here. So that's why it is a memory element. Same way, if you put R equal to 0 and S equal to 1, you program it to be in the reset state here. And once you remove this particular input from 1, 0 to 1, 1, it retains its state here. It retains its state Q and Q bar here. So that's why it's a memory element. You can program it to be 1, or you can program it to be 0. 1 is set state and reset state here. And then when you remove those inputs and keep the S and R equal to 1, then it will retain this state here. Whatever was the state, it will retain it here. Now, we had seen that enable is a very useful feature in combination circuits. By adding a enable input, we can take a particular piece of circuit and using that enable input, either disable it or enable it. We could do the same thing with our NAND latch here. We could add an enable input like this here. And so this is our basic cross-coupled NAND latch here. And we're adding an enable input through this NAND gate here and feed in S here and R here. So note that it's easy to see that when enable is 0, so when this is 0, the output is 1, 1, and therefore my latches will remain in the hold state here. Whatever, so no matter what I apply at S and R, these two inputs will not change here, and the latch will stay in its original state here, or the present state, Q and Q bar here. So it's the whole state here. The moment you put enable equal to 1, now the S will go through. So note that we said that once you put one input of the NAND gate as 1, then NAND gate acts as an inverter. So S becomes S bar here, R becomes R bar here. So the moment you put enable equal to 1, so we get S bar and R bar, and the NAND latch works in the manner that we discuss here. And now the whole thing becomes active when S is equal to 1. So earlier the NAND latch, we had to put S equal to 0 to program it into Q state here. So now we can put it equal to 1, and then this will become 0, and therefore it will put it in the set state here. So once the enable is 1, S equal to 1 puts it into the set state here. R equal to 1 with S equal to 0 puts it in the reset state here. 0, 0 is as usual, is the whole state here. And once again, 1, 1 is an input that we do not allow. Right, so this is the NAND latch with an enable input. And now it works just like a NOR latch earlier. With S is equal to 1, programs it into, with S equal to 1 and R equal to 0, programs it into the set state. With S equal to 0 and R equal to 1, programs it in the reset state here. And with S equal to 0 and R equal to 0, stays in the whole state, and the other input is not allowed. Okay, so SR latch is one kind of a latch. There are other kinds of latch also, and another very popular kind of a latch is D latch here. And one way of thinking of D latch is that if you have SR latch here with an enable input, let's say, so what we can do is we can combine S and R through this inverter here. And so now the operation is very simple. We can see that once the enable pin is, if it is 0, then of course the latch stays in its whole state. So let's put enable equal to 1. So when enable equal to 1, if you put D equal to 1 here, then S is equal to 1, R equal to 0. So Q becomes equal to 1 and 0 here. So basically whatever is the data here, if it is 1, it goes to here. Similarly, we can see here. So if enable equal to 1, Q equal equal to D here. So if on the other hand, if D equal to 0, S would be 0, R will be equal to 1, and therefore Q will be 0, and Q bar will be equal to 1. So basically, the output Q is equal to the data once the enable pin is enabled here. So whatever is the data that is coming in here, the same thing is latched once the enable is 1. And once you disable the enable, well, the latch will retain its state that is there here. Okay, so that's a very simple, very useful latch. And operation wise, it has only one input, D, and Q equal to D once the latch is enabled. Now, so these latches are very useful, and we can now combine them with combinational circuits to make circuits which we call as sequential circuits. And so sequential circuits, as we discussed, are nothing but combinational circuits with some feedback, with direct feedback or feedback through storage elements. And in this context, when we are building sequential circuits and with feedback amongst occurring, it is convenient that we have a signal called a clock signal here. And the idea of a clock signal is that it synchronizes everything in the circuit takes place in sync with the clock here. And so the idea is that, if you have a combinational circuit and we know that the signals may come at the input of the combinational circuits with different amounts of delay. And not only that, there's a feedback also. And unless we take care of all the delays that are there in the circuit, we may end up getting wrong values at the output. And and in that case, if we make sure that everything happens in sync with the clock, then we can make sure that all the circuit behaves according to the behavior that we desire here. So the idea is that the clock, for example, so the clock is nothing but a periodic signal that you see here. Okay, and the idea is that, for example, when the clock is high, let's say when the clock is high, the data is stable. Data X, for example, that we feed in is stable here. And when the clock is low here, well, the data can change. Data can change, but when the clock is high again, the data is stable, right? So what we are saying is all signals are in sync with the clock. And so the data is in sync with the clock. So the data is a stable data when the clock is high. And if you want to change the data to some other value, well, it can change in this particular period here. In this part here, the data can change. So that's where we are describing the change. But the moment it becomes high, a little bit before it becomes high, the data should be stable again. And by ensuring that the data follows the clock in this particular manner, not just one particular data, but all data. So we are making sure that all data, when the clock is high, all data are stable. All data are stable because all data has to follow the clock. And so all data are stable, and therefore the outputs of the gates and everything else would be stable when it is evaluated in this particular period here, in this particular time period here. And everything is evaluated here. While in this particular case here, you note that data is changing, and the data would be changing with different delay values. So in this period, the outputs of gates and all that would be, you may undergo more than one change value, it can change more than once. While in this case, it is all data are stable here. So if you feed in the data, let's say one data X comes into an AND gate here, another data Y comes into an AND gate here, well, the output of the AND gate would be stable here. On the other hand, if you look at the output of an AND gate here, well, X may be changing and Y may be changing, and they may be changing with different delays, and therefore the output of the AND gate is unpredictable. It may change once, it may change twice, it may change 3 times, depending on how the data is changing here. So the idea is that when you have a complicated circuit, the use of a clock makes sure that there is a time period available where the data is stable. All data are stable, and they have their proper values here. So the clock is like, you could think of it as an analogy like a orchestra, where the conductor according to the cue from the conductor, all the musicians, they play their instruments according to the cue from the conductor here. So in this case, everything happens in the sequential circuit. Everything happens according to the clock that is there here. Is synchronizing all changes in the circuit according to the variation in the clock that you see here. So clock is an essential element of most of the sequential circuits, and we call those sequential circuits as synchronous. Synchronous meaning everything takes place in synchronous with the clock here. All right, and clock is nothing but a periodic signal that is available everywhere in the circuit. Okay. All right, so for example, we could say this is the first clock period, this is the second clock period, and so on and so forth. This could be the nth clock period, and the data that is available here, we can call it xn here. The value of x in the nth clock period here. All right, so let's look at some examples here. So let's say we have a circuit like this, and so these are the inputs A and B and C n, and we have the outputs, let's say Zn and Yn here, and we have a storage element, and we see a feedback loop also. All right, so let's see what happens according to the clock here. So let's say An goes like this here, Bn goes in this particular manner here, Cn goes in this particular manner here. So how does this particular circuit works here? So we look at Y, and the value of Y will depend on the D here, right? So let's look at, so Bn is 0, Bn is 0 here, and Cn is 1, right? So this is 0 here, and get here 0 here, and initial value of Y is 0 here, Y is 0 here, and so 0 and 0, so this is 0 here, and if this is 1 here, so this is equal to 0 here. Let's say this is 1, so An is 1 here, and this is 0 here, right? So it stays 0 here, Y stays 0 here. And then let's come to the, note that the clock is being fed to the enable input of the D latch here. So only when the clock is high, that the data here can change here, okay? That the data Q can change. Otherwise, when the clock is low, nothing will happen to the output Y here, okay? So again, let's look at when the clock goes high, and the clock goes high here. So, all right, so this is there. Okay, so let's now Bn is 1 and Cn is 1 here. So this 1 and 1 will make it equal to 1 here. And Yn equal to 0. So far it is 0. So this 0 goes here. And 0 and 1 will make it 1 here. Right? We'll make it 1 here. And this is 1. An is 1 here. So that goes to 1 here. And note that this input is 1 and the clock goes high now. Clock goes high, and then therefore clock goes high, so Q goes, all right, so Z goes 1 here, and so Y goes high here, right, after a certain delay. Know that it takes a certain amount of delay, so when the moment the clock goes high, this goes high here, and the moment this goes high here, note that if this goes high here, 1 here, so it 1 here, and then the Z goes 0 here. So look at what happens here. All right, so this was 0 here, right? This was 0 here, and this is 1 and 1, so Z is equal to 1 here, right? So Z is 1 here. But then the moment the clock comes in, the state of Q changes to 1 here, and this goes to 1 here, this goes to 0 here, and this goes to 0 here, right? So that's how it behaves. Okay. All right. Now, the latch that we've been talking about is a latch where as long as the clock is high, then Q follows whatever happens at D. Any change in D results in a change in Q. And that can cause a problem in many of the circuits. And that can be illustrated in a very simple manner with this particular example here. So circuits are designed with the idea that there would be a single change in output or memory state in a single clock cycle. The whole idea of a clock cycle is everything takes place in sync with the clock cycle, and also one single change in one single clock cycle. Otherwise, if we allow more than one change, then again there's a chance that the output will become unpredictable depending on, again, the delays in the circuit that are there here. And that can still happen even though we have a clock when we use a latch like this here. So let's see what happens here. So let's say clock is like this here. And so clock is like this. So initially y is 0. Let's say y is 0 here. And so what happens is y equal to 0 here, and 0 and 1 will give rise to 1 here. And then because clock is high, so this will go to 1 here, right? It will go to 1. After a certain delay, it will go to 1 here. But then once it goes to 1 here, this is fed back again here, and 1 and 1 will generate a 0, and then the 0 will also go there because the moment clock is high, Q is equal to D. So it will go to 0 here, and then it may go up here again, and it may go down here again, right? So what is happening is, and we don't know what will be the final value. Will it be equal to, because the moment the clock goes to 0, now the latch stops to respond to any change in the input here. So the moment clock goes to 0, now will it be equal to 0? Well, that depends on what the delay of this particular circuit is, right? So if here, for example, if we had less delay in this particular one, maybe it could have gone from 1 to 0 to 1 to 0, and maybe it could have gone to 1 again. And then maybe the output would have been 1, right? So again, because of the delays that are there in the circuit, and the delays are unpredictable, what the delays are likely to be, we don't know what the output of this particular latch is going to be. And so this problem is occurring because once the clock is high, then Q is simply equal to D. And also we have these sequential circuits where we have this feedback loop here. So once the clock is high, the signal can go here, and then the signal can go into the input side here and again modify it, and thereby result in multiple changes in the value of Q, and thereby make the value of the latch output unpredictable. And so this particular problem can be avoided if we make a clock. So this is what we are saying here. So Z also, so if Y is changing like this here, then Z also changes like that here. So this is avoided by making a latch which is not, so in this case we are saying the latch gets enabled when the clock is high. So we call this latch as a level triggered. So when the level is high, when the clock level is high, then Q equal to D. When the clock level is 0, then it retains its original state. It's in the whole state here. So we call this latch as level triggered. In the next case, we are talking about the latch which is edge triggered. And the edge triggered latch is also, we have another name for it, which is called a flip-flop. And we describe it using this particular symbol here. So this, when we have a clock here and we put this symbol here, it becomes it's a edge triggered latch. And we don't call it edge triggered latch, we use a shorter name called flip-flop here. And so the idea is this. So it is edge triggered, meaning it is 0 to 1 transition. This is the edge of the clock here. So we have two edges here. This is called the positive edge here, when we are going from 0 to 1. And when we go from 1 to 0, we call the negative edge of the clock here. So this is a positive edge triggered flip-flop here. So the idea is as follows. So let's say we have a clock here, and because it's edge triggered, we show it with an arrow here. It's positive edge triggered. And let's say the data goes in this particular manner here. So now, whatever is the data just before the positive edge, that's the data that goes into the latch here. So Q equal to D, and D, which was just before this particular positive edge triggered here. So Q will be, so note that Q will be, let's say Q is 0, And just before the positive edge triggered, the data was 1, so it goes into 1 here with a little bit of delay there. Now again, you look at what happens before this edge here. So the data is 0, so it goes 0 here. In this case, again, you note before what happens before this particular edge here. The data is 1, so it goes 1 here. Now note that in this case, the data is changing. It goes from 1 to 0 and then back to 1. But the latch does not respond. The latch will only respond to what happens just before the edge here. So just before the edge, it is 1. So it stays 1 here. So all the change that occurs here within the clock period, all the change is ignored. Whatever is the data just before the positive edge here, that is the data which is latched here. And so this is what we call as a edge triggered latch, or we call it as a flip-flop. Of course, there is certain limitation. We have to keep the data stable for a little bit of time before the positive edge comes here. So during the design, we have to make sure that our data is stable. It's not changing very close to the positive edge trigger here. And we call that as the setup time of the flip-flop. So the data has to be set up properly before the positive edge trigger within a time period called the setup time. And within, so let's say the setup time is 1 nanosecond. So 1 nanosecond before the positive edge trigger, the data should be stable. If you want data to be 0 to be latched, well, the data should be stable and 0 within 1 nanosecond here. Okay. So that's a positive edge triggered flip-flop. And negative edge triggered flip-flop, we show it using an arrow here. So that responds to whatever is the data just before the negative edge, that goes into the latch here. Q will be equal to D just prior to the negative edge here. So in this case, Q is here. So just before it, so if it is initially 0, it stays 0. Just before the negative edge is 1, so it goes 1 here. Just before the negative edge is 0, so it goes to 0 here. Just before the negative edge is 0 here, so it stays 0 here. So that's a negative edge triggered flip-flop here. So let's look at how we can make a negative edge triggered flip-flop, basically using 2 latches here. And in this particular design, we use 2 latches. One of them is called a master latch and the other one is called a slave latch here. And so both of them are simple level triggered latches here with an enable input here, enable input here. And this is a clock signal. And so what we have to show that the data which is eventually latched is the data which is present just before the negative edge comes in. So let's say we have a clock like this here. And for the sake of discussion, let's say this is the data that comes in here. Okay, so the main data is over here. And so we note that this master here will respond, the output of the master will be equal to the input here as long as the clock is high here. And so what happens is, and the moment the clock goes low, the master is disabled and whatever was the value of Q, that is retained at the output here. So if D goes like this here, so note that D is high here, so output would be high here. Master, if we look at output, would be high here, but then D goes low here, so the output will go low here. But the moment the clock goes low, then whatever was the value of the D just before the clock, before this negative edge here, that's the value that goes, that is the output of the master here. And once the master is disabled, then the slave is enabled here. So the clock goes low and then this signal goes high and then the slave is enabled here. And the value of this will be equal to basically whatever is the value here. So whatever was the data that was latched onto the master's output, which is the data just before the negative edge, the same data now is transferred here. So basically then master goes like this here. So we know that master's output would be basically equal to the value of D. Master will follow as long as the clock is high, master will follow D. And the slave here, so slave part here, we can see here that the moment the clock goes low, the slave gets enabled and whatever is the value of the master, that gets latched here. So that's the value 0 here, so it stays 0 here. And then again a negative edge comes, and the moment the negative edge comes, the slave gets enabled here, and so slave looks at its input, and the input is high here, and therefore it goes high here, right? So effectively, this whole combination is made up of a level triggered. So each one of them is level triggered here, but overall the output here responds to whatever is the data just present before the clock edge here, negative edge clock edge. Okay, so that's called the master slave D-type flip-flop here. There are other ways in which we can make the and we denote it by this particular symbol here, right? So we said this symbol here is a edge triggered flip-flop, and the bubble here denotes that is a negative edge triggered flip-flop. There are other ways of implementing a edge triggered flip-flop. So this one is a positive edge triggered flip-flop. So it's a little bit complicated looking circuit, but let's see how it operates here. So let's say initially the output Q equal to 0, and this is 1 bar, 1 here, and clock is initially 0. So if it is 0 here, let's say the data that we want to go, so we want to program this flip-flop, Q should be equal to D the moment positive edge trigger comes here. All right. Okay, so with this value here, when the clock is 0, then 0 here, NAND gate output is 1 here, this is 1 here, and so this particular latch is basically in a hold state here. It's in a hold state here, and note that you know, you could change anything here, but because the clock equal to 0, so it forces equal to 1. So this whole thing does not respond to any changes in D. You can make D 1, 0, anything you can make here. This output, these two outputs will always be 1 because the clock is 0 here. And therefore, the latch is in a hold state here. So let's, all right, so this is D equal to 1 here, and fine. Let's change the clock, goes from 0 to 1. Now, the moment there's a clock, there's a positive edge, so it goes 0 to 1. And 0 to 1 here, so this S goes from 1 to 0 here. Why does it go from 1 to 0 here? Well, note that because D is 1 here, and this is 1 here, so 1 and 1 0 here. So this 0 is coming here, so this is 1 here, and this 1 here and 1 here, so 1 1 here. So the moment 0 to 1 here goes, this goes to 1 to 0 here. 1 to 0 here makes it go to 0 to 1. Okay, so we wanted, because D is 1, we wanted Q to go to 1 here. So that happens the moment the edge comes. This goes 1 to 0, this goes to 0 to 1. Now, of course, this will go to 1 to 0 here. So at the moment this goes 1 and 1 and 1, so that will force it to 0 here. Okay. And note that fine, the clock has now gone from 0 to 1, so now it's in a stable 1 state. And you can change the input here. Change in input here. You can make D go from 1 to 0 here. Let's say it goes to 1 to 0 here. This goes 0 to 1. But note that this goes to 0 to 1, but nothing happens to the output here. You can verify that nothing changes at the output here. 0 to 1 here, and so this is 1 here, and no change occurs at this input here, because as it goes to 1 here, so note that 1 here, and this was 0 here, so this stays at 1, and 1 and 1 makes it 0 here, so no change occurs here. So it only responds to changes when it goes from 0 to 1. And at that point, whatever is the value of the D here, then is able to affect the value of Q here. Otherwise, once the clock reaches the stable state of 1, after the clock reaches a stable state of 1 and you change the value here, it doesn't change. When the clock is in 0 state, then of course nothing, the latch is in a hold state. When the clock is in 1 state, if you change anything, it doesn't change anything here. All right, so this is also a edge triggered, and any edge triggered latch is called a flip-flop. So it's a positive edge triggered flip-flop. In this case, what we have done is we've taken a positive edge triggered flip-flop, but we've added a reset input also. So for example, there may be a memory element which responds to the clock and whatever is the data just before the positive edge gets latched here. But there may be times when you want to reset everything to, let's say, 0, all the memory to 0 here, and independent of the clock. right? So that is called the asynchronous reset here, or asynchronous clear. Asynchronous means it doesn't depend on the clock. The moment reset will go high, the output will go 0 here, independent of the clock here. So reset is 0. Note that if reset is 0, this is 1. And in this case, it is active low here. So when reset is put equal to 0 here, so this 0 goes here, 0 will make it 1. And we've seen that when S is equal to 1 here, it forces the output Q to go to 0 here. So we denote it by that the reset pin or the clear pin is active low. If reset equal to 1, note that when a 1 goes into a NAND gate, that 1 doesn't do anything to the NAND gate here. It's only a 0 which forces the output of the NAND gate to go to 1. When it is 1, it depends on what the rest of the inputs are, and therefore it depends on the clock here, right? So that's a positive edge triggered flip-flop with the asynchronous reset pin here. Similarly, one could add a positive edge triggered flip-flop with the asynchronous set pin here. So if you want to set a flip-flop to 1 independent of the value of the clock, and so we can do that also. So that is called a presetting the value equal to 1 of a particular flip-flop. So many flip-flops are designed with a asynchronous reset or a asynchronous clear or a asynchronous preset input also. So when we talk about flip-flop, we have a concept called characteristic table. So that just like a truth table describes a combinational circuit, similarly characteristic table describes a flip-flop. So basically what it says is that given the inputs that are there to the flip-flop, in this case it's a D flip-flop, given the inputs and the present state of the flip-flop, what will happen to the next state of the flip-flop when the clock edge comes here. So in this case it's easy. So input is D here. So if the input is 0 and doesn't really matter what the present state is, the output will go to 0 here. So that's the nature of the D flip-flop. The moment clock edge comes, whatever is at D goes to Q. And similarly, if the input is 1, the output goes to 1 here. So QT plus 1, the next state only depends on the data here. Doesn't depend on the past value here, whatever is the past value here. QT plus 1 equal to D. There's another flip-flop called JK flip-flop here. And JK flip-flop's characteristics are as follows. So when it is 0, 0, the JK flip-flop is in the hold state. So QT plus 1, the next state is same as QT, which means that if J equal to 0 and K equal to 0 and a clock edge comes, a positive edge comes here, well, Q will remain equal to its previous value. If J equal to 0 and K equal to 1, we call it the reset, the flip-flop gets reset. When J equal to 1 and K equal to 0, the flip-flop gets set. And when J equal to 1 and K equal to 1, the flip-flop toggles. Toggles means it flips. So QT plus 1 is QT bar. So initially if it is 0, it will become 1. If it is 1, it becomes 0 here. So we call it a toggle. It toggles from 0 to 1 or 1 to 0 depending on what its previous state was. And we can describe this particular table using this particular equation here. And so basically, we could write a truth table like this here. We could write a truth table, say JK. We could write it here, and we could write Q here, right? Q is 0 and 1. This is 0, 0, 0, 1, 1, 1, and 1, 0. And so we can fill it up. When JK is 0, 0, QT plus 1 is 0, so this will be 0 here and will be 1 here. When JK is 0, 1, when JK is 0, 1, output QT plus 1 is 0. So 0, 1 is 0. When JK is 1, 1, when JK is 1, 1, then it flips. So Q is 0, output is 1, Q is 1, this is 0 here. And with 1, 0, the output is always equal to 1 here, right? And therefore, we need to write down then what is, so you can see here, we can encircle this one, and we can encircle this one here. and this one will give rise to basically equal to Q bar because Q is common, and we write it as J, and this term that we write is Q, and what is common is K bar, right? So that's how we get basically this equation here. Okay, so we can so that's the JK flip-flop, and is characteristic table. Characteristic table meaning given the present inputs and given the present state, what will happen to the next state when the clock edge comes here, right? So the possible inputs are 0 0 0 1 1 0 1 1, and this is what will happen to the flip-flop when the clock edge comes, and this can be described by this equation here. So like a truth table, this is the characteristic table for a flip-flop here. And there's another flip-flop called T flip-flop or toggle flip-flop. So this also has only one input, and as its name indicates, if the T input is 0 and the clock edge comes, well, the output becomes output is same as input. Output is same as before. Qt plus 1 is Qt. On the other hand, when T is 1, then the output toggles. If if Q is 0, then it becomes 1. And if Q is 1, then it becomes 0 here. So that's where it gets the name toggle here. But that happens only when T equal to 1 here. If T equal to 0, then it's like in the hold state here. And so it's easy to write Qt plus 1 is equal to Qt bar T plus here. We can write it this characteristic equation here. Then there is this concept of what we call as an excitation table. We'll see the value of this excitation table in the next lecture when we design sequential circuits. So the idea of excitation table is the following. It says what inputs are required to cause a particular state change. Okay, so meaning, let's say we have present input Qt equal to 0, and you want to go to the next state which is equal to 0. What input should we apply? So in the case of T flip-flop, well, we can apply 0. If we apply 0, then we know that the T flip-flop is in the hold state here. On the other hand, suppose your present state is 0 and you want to go to Qt plus 1, which is 1. So what input should we apply to T? Well, the answer is 1. If you want to go from 1 to 0, again you should apply 1. If it's 1 1, then it's 0 here, right? Well, what would be the excitation table for JK flip-flop? So excitation table means what input should we apply to cause a particular change in the output here, particular change in the state. So you want to go from 0 to 0. So what input should we apply? So now 0 to 0, we know that it's like the hold state here, right? So we can apply J equal to 0 and K equal to 0. But we also note that the final output Qt plus 1 is 0. So we could also apply 0 1 because 0 1 will also force it to 0 here. So there are two possibilities. We can apply 0 0 or we can apply 0 1 and the output will be equal to 0 here. The next state will be equal to 0 here. Now 0 0 and 0 1 can be combined and we can say, well, if we apply 0 and K is don't care. You can apply 0 here, you can apply 1 here, and this will cause this kind of a transition here. To cause a transition from 0 to 1, well, 0 to 1, well, what do you have to do? Well, 0 to 1, you have to apply 1 0. So if you apply 1 0, then the output will go to 1. But because 0 to 1 is also toggle, you can also apply 1 1. And therefore, the input required to cause this kind of a change can be, if you combine these two, 1 0 is a possibility and 1 1 is a possibility. It means that K doesn't really matter. All you have to ensure is that J equal to 1. So J equal to 1 and then don't care state here. And 1 to 0 is the opposite. So this is equal to 1 here. And 1 to 1, well, 1 to 1 means if you apply don't care and 0 here. So this is the excitation table of the JK flip-flop here. And the excitation table for the D flip-flop is the simplest. So you want to go from 0 to 0, the input is 0. You want to go from 0 to 1, the input you apply 1. 1 to 0, you apply 0. The present state is 1. You want to go to next state 0. Well, simply apply that particular data here, 0. 1 and 1, you apply 1 here. So the excitation table of D flip-flop is very simple here. So we have various kinds of flip-flop, and it's if you have a D flip-flop and you're looking for a JK flip-flop, well, you can convert a D flip-flop into a JK flip-flop. Similarly, if you have a JK flip-flop and you're looking for a D flip-flop, you can convert them also. So the basic idea is as follows, that you have a D flip-flop available to you. So whatever flip-flop is available to you, so let's keep that. And you want to convert it into a JK flip-flop. So what we do is, you want to convert it into a JK flip-flop, we add a combinational circuit. So the idea is that using JK will generate a value of D such that the output then Q goes into a state in correspondence with the value of J and K here. So this combination circuit is something that we have to design. Okay. So let's see how we can do that here. So we know that if J equal to 0 and K equal to 0, QT plus 1 should be equal to QT, right? So what value of D should we put here? What value of D should we put here? So what should be the output here? Well, D should be equal to QT, right? D should be equal to QT. If the Q is equal to 0, then D should be equal to 0. If Q equal to 1, then D should be equal to 1 here. Fine. If J is equal to 0 and K equal to 1, well, then that's called the flip-flop should get reset. So QT plus 1 equal to 0. So D should be equal to 0. That's fine too. If it is 1, 0, QT plus 1 should be 1. So we should put it equal to 1. If you have 1, 1, then we should put it, D should be equal to QT bar here. Right? So now we have to determine, note that D has to be determined. D is the output of the combinational circuit. So D has to be determined in terms of J, K, and the present state here, Q. So JK 0, 0, 0, 1, 1, 1, 1, 0, and Q present state here. And so we fill up this table here. Well, how do we fill it up? See, note that JK is 0, 0. So let's look at 0, 0. And we are saying D equal to QT. So when Q equal to 0, D equal to 0. So we are trying to determine D is the output of this combination circuit. So we are trying to determine an expression for D. So D equal to QT, so we put 0 here and 1 here. For JK equal to 0, 1, well, D equal to 0. So we put in 0, 0 here. For JK equal to 1, 0, D is 1. So we put 1, 1 here. And for JK equal to 1, 0, JK equal to 1, 1, we put QT bar here. So 1, 1, we put, so Q equal to 0, we put D equal to 1. Q equal to 1, we put D equal to 0 here. So that's the truth table that we get, and then we can combine them together and we get D should be equal to Q bar J plus QK bar here. And therefore we can implement as follows here. We have a D flip-flop, and we generate this particular term, Q bar J. So we take Q bar from here, so this is Q bar J here, and K bar here, so we take Q from here and K bar here. So we generate these two, we add them up using an combine them using an OR gate and feed it into D here, right? So that in this particular manner we can take a D flip-flop and convert it into a JK flip-flop here. So like that you can given any flip-flop, you have a flip-flop 1, you have a flip-flop 1, and you want to convert it to some other flip-flop. It has some inputs here. So you add a combinational circuit here, CC. Some combinational circuit whose inputs are the new flip-flop that you want to convert. So the new flip-flop's inputs are, let's say, X1 and X2. And along with that, you have available Q and Q bar here. So that's also, that is there here. Right? So this is the old flip-flop, let's say Y1 and Y2. This is the old flip-flop whose inputs are Y1 and Y2. This is the new flip-flop whose inputs are X1 and X2. And what we now have to determine is what is Y1 as a function of X1, X2, and Q. And what is Y2 as some function F1 and F2 as X1, X2, and Q here. And thereby we have the new flip-flop here. Okay, so any flip-flop, old flip-flop, let's say you have a flip-flop 1 and you want to convert it into flip-flop 2, new flip-flop whose inputs are X1 and X2. So that's what you have to do. Take the flip-flop that you have, add a combinational circuit to it, and then determine what the outputs of this particular flip-flop has to be in terms of these particular inputs, X1, X2, and Q here. And the procedure we have illustrated using this particular example here. Right, so let's stop here and we'll continue and then look at how we can, using these flip-flops, design more complex sequential circuits.